Hello, in this video we're going to talk about projecting vectors onto a subspace. And in the previous video we talked about projecting a vector onto another vector, and one way to think about that is that we are taking a vector, say u, and finding a vector parallel to v, so that's on the line spanned by v, such that the difference between those two vectors is orthogonal to v. And we can actually do the same thing, not just with a line, but for any subspace of Rn, and that's what this video is about. So let's say that you have W, a subspace of Rn. And let's say that U is a vector in Rn. Then it turns out, so the fact that we're going to talk about is that every vector U can be written as W1 plus W2, where W1 is an element of W and W2 is orthogonal to the subspace W. Now what does orthogonal to subspace mean? It means that it's orthogonal to every vector in W. In particular, it's orthogonal to W1. Right, so every vector U has this form W1 plus W2, where W1 is in W, and then this W2 has the property that W2 dot W1 is 0. Okay? And it's actually orthogonal. W2 is orthogonal to every vector in W. And to get an idea of how this works, let's just do an example with R3. So the idea is to use what we did in the previous video, the same method. Oh, how come this pen is not working? Is that on the battery? Hello? Okay, let me switch pens. Okay. So let's say I have the vector u, which is 1, 2, 3, and w is a plane in R3, and it's spanned by the vector 1, 0, 0, and 2, 2, 1. Okay? And the question is to compute the projection of U onto the subspace W. And, oh, by the way, this W1 is called the projection. Okay, let's put this on the side. W1 is called the projection of U onto the subspace W. Okay. And notice that instead of a single vector, right, previously we had projection of U onto a vector V, but this time we're talking about a subspace. Okay. And what we talked about before about projecting a vector onto a vector V, that's a special case of what we're talking about now, where the subspace was a line. Right? Here we're talking about just the general subspace. In this case, in this example, it's a plane in R3. So what's the projection of U onto W? Well, so let's call this first vector this first vector 1, 0, 0. Let's call that V1, and let's call the second vector V2. Okay? Well, so what we're looking for is we want the projection of u onto w, well, this is going to be a linear combination. This is a vector in the subspace W, right? So it's a linear combination of v1 and v2. So it has the form c1 v1 plus c2 v2. So with the property that u minus this vector is orthogonal to both, well, it's orthogonal to W. In particular, it's orthogonal to both V1 and V2. And actually being orthogonal to W is equivalent to being orthogonal to V1 and V2, because if you have a vector that's orthogonal to V1 and V2, then it's orthogonal to any linear combination of V1 and V2. That's just from the dot product property, right? The distributive property of the dot product. So what we need is, we need this vector. When you dot it with V1, you should get 0. And when you dot it with V2, you should also get 0. So let's write those equations down. So U minus, let's put parentheses here, C1 V1 plus C2 V2. You need this dotted with V1 to be 0. And we also need that the same vector dotted with V2 is 0. Well, let's distribute this out. So this is going to give you, this is equivalent to writing U dot V minus parentheses C1 times V1 dot V1 plus C2 V2 dot V2 is equal to 0. That's the first equation. And then the second equation is equivalent to, oh, that's a V1. The second equation is equivalent to U dot V1, U dot V2 minus parentheses C1 V1 dot V2 plus C2, oh, oops. This should be a V1. Okay. C2 V2 dot V2 is equal to 0. Right? And now what we have, look at what we have. We have these two equations, and this is a constant. We're solving for C1 and C2. V1 dot V1 is a constant, V2 dot V1 is a constant. I have these constants here, here, and here. And I'm solving for C1 and C2. And so what I have is a system of linear equations, which I know how to solve, right? I mean, this is going to give you, when you just add this and this to both sides, you're going to get V1 dot V1 C1 plus V2 dot V1, or it's the same as V1 dot V2, of course. C2 equals U dot V1, and then the second equation is V1 dot V2 C2 C1 plus V2 dot V2 C2 equals U dot V2. And this is a system of linear equations I can solve for C1 and C2. And by the way, in case you didn't already figure this out, the reason why I wrote it in a different order is because I'm trying to solve for C1, right? And so I have this constant times, if I think of C1 and C2 as like a variable, then it's consistent with how we typically write 2x, for instance. Okay, so that's what we can do to solve for C1 and C2. Well, let's just do it out in this particular example. So I did that somewhere. Yes, if you calculate this out in this example, so what this is very general, right? But when we plug in these specific U and v1 and v2, the system ends up being c1 plus 2c2 equals 1, 2c1 plus 9c2 equals 9. Okay, just calculate the dot products and this is what you get. And then we can solve this system. So we would write this as, well, this second equation is 2c1 plus 4c2 equals 2 after you multiply it by 2. And then when you take the second equation minus 2 times the first equation, you're going to get c1 plus 2c2 equals 1, 5c2 equals 7. And therefore, c2 is going to be 7/5. And c1, when you plug it back into the first equation, you get negative 9/5. And so therefore, the projection of u onto onto w, well, that's c1 v1 plus c2 v2, and that's going to be negative 9/5 times v1, that's 100, plus c2, that's 7/5 times 221, and now we just need to do the arithmetic. The first component is negative 9/5 plus 14/5, that's 5/5, that's 1. Second component is 0 plus 14/5, and then the third component is 0 plus 7/5. So that's the answer. The projection of u onto v is this vector. Okay? And that's how you can find the vector on w. That's the component of the component of u on the subspace w. And then to find the vector that's orthogonal to this vector, you just do u minus this vector, right? Okay. So for instance, if the question asks you to decompose the vector u into a sum, this would be your w1, and then your w2 is u minus w1. But this question just asks for the projection of u on the subspace. Now, if you look back at the calculations we did, right, we had a system of linear equations to solve, which is here, this system. Now, if you look at this, suppose, in this example, v1 and v2 were sort of just random, but suppose that v1 dot v2 were equal to 0. Suppose that we had orthogonal vectors. Well, in this case, that v2 dot v1 and v1 dot v2 would both be 0. And then you get, so this first equation would be v1 dot v1 c1 equals u dot v1. So in that case, then you can divide both sides by v1 dot v1 and get that c1 is u dot v1 divided by v1 dot v1. Does that look familiar? That was the constant of v when you project u onto v. And if you take the second equation, it's v2 dot v2, c2 is u dot v2. If you divide both sides by v2 dot v2, you get that c2 is u dot v2 divided by v2 dot v2. So the calculations become a lot simpler if you had orthogonal vectors that spanned w, right? If we had vectors that were orthogonal. And notice that when you change the vectors to be orthogonal, as long as the span of those vectors that you have is w, the answer is not going to be affected, right? Because you're working with the subspace w. I mean, the only relevance of these vectors was that they lied in w, they spanned w, and you can use those to calculate the projection. But what if w was spanned by, two other vectors? Well, but you have the same w. Well, then you'll get the same projection of u onto w. Right? So the question now becomes, okay, could we replace, how do we replace the V1 and V2 that we have to get something that's orthogonal but somehow still spans W? And if we do that, then we can come up with a different method. I mean, we just do the same thing, except the constants would be a lot easier to work with. So that leads to something called the Gram-Schmidt procedure, which is when you have a basis for a subspace. So in this case, the set V1, V2 is the basis for W. How can you replace that with an orthogonal basis? So one where all the vectors are orthogonal to each other. And then there's a next step to make all the vectors unit vectors that simplifies it a bit more. I mean, if you had unit vectors, then v1.v1 here, the denominator would just be 1, and v2.v2 would be 1, and that makes this even simpler. Your c1 would just be u.v1, and your c2 would be u.v2. So we'll talk about how to do that in the next video. Okay, thanks for watching.